Okay, the next part of this topic that we're going to be looking at is bounds. Bounds, and it's kind of short for boundaries of lengths and weights and things like that. It's all to do with rounding. So if we were to just take, I don't know, something like a room, someone's room, and let's say that was 5.4 meters in width or length or whatever you might call it. So let's say 5.4 meters width. Someone has actually told you this 5.4 meters. It means that they've rounded it themselves, because they might have read on the tape measure something like 5.42 meters, and they said, well, I just want one decimal place, so here's the first decimal place rounded. That actually makes 5.4 meters. So you can see that 5.42 meters actually is 5.4 meters, but also what about 5.37 meters or something like that? I'm just making these numbers up to show you as an example, but if we wanted to round that to one decimal place, well, we take the 3 as the first decimal place, and the 7 means that we round the 3 up. So we round it up to 5.4 meters. So although these distances, or these lengths here of the room, or the width of the room, are very different, that's actually a 5 centimeter difference, which can be quite, if you look on your ruler, can be quite large, I suppose. It actually rounds to exactly the same distance to one decimal place, and that they're actually, if we were to think about it, 5.4 meters can be anything from as high as 5.4499, so on and so forth, because this means that it would round down to 5.4. So what we'd like to do, instead of 499, what we'd do is anything up to 4.45, because it's very close to that, means that we could round it down to 5.4. So 5.45 would round down to 5.4, although technically speaking that 5 should mean that we'd round up, but it can get so close to that we might as well just call it 5.45. That's the key thing to know there. But what about the lower limit of this? Well, the lower limit could mean that it could be down to 5.35. So anything above 5.35 and below 5.45, so this range of values here would mean that we get this 5.4 meters to one decimal place. So that's what we call the bounds, and actually this here is called the upper bound, so the highest value, and this here is called the lower bound, which is the lowest value that it could possibly be. Before, if the actual length was 5.34 to one decimal place, that would actually round down to 5.3. So you can see that the bounds represent the actual values of the measurement or whatever it might be. That means that it would actually round to that first decimal place, or it might be the second or whatever, but in this case it's the first decimal place. Okay, so what about then if we had the length or the other width of the room, the other measurement, and let's say that was 4.5 meters in this case. So I'm just going to clean this up a bit. I can delete that a little bit. You can always wind the video back if you need to see it. So this bit can stay here. So what are the upper and lower bounds of this? And I'll do this in blue actually. This 4.5. So here we go, we've got 4.5 meters, and we'll say that the upper bound and the lower bound are which? So the upper bound and the lower bound. Well, the 4.5, the upper bound of that would be when 4.5 and the second decimal place gets to the point where anything more would mean it would go higher. So 4.55, anything more than that, technically speaking, I suppose we should include the 5, but as I mentioned earlier, we'll keep 4.55 is the upper bound, because anything higher than that would mean that it would be 4.6. However, the lower bound is 4.45, because anything lower than that would be 4.3 as a rounded 1 decimal place value. So these are the ranges. Anything between here, we would be getting 4.5 as that length. So the next step, the next question that could come up, if I just put that up there, is what are the upper bound of the area and lower bound of the area of this particular room? Well, what does that mean? Well, normally when we're finding the area, we just take the width, take the length, and in fact I'll do this in green. There we go. So 5.4 and 4.5. We'll take those values and we'll just times them together. So we'll just do 4.5 times by 5.4, and that equals. Let's just see what that equals. 24.3. And remember, this is an area, so that would be meters squared. 24.3 meters squared. Okay, so that's how I would normally do it. But what do we mean by these upper bounds and lower bounds? Well, area is equal to width times by length of a rectangle or something like that, some quadrilateral shape. But for this one, area equals width times by length. So the upper bound for the area would be when the width and the length are at their values that will make the area the largest number possible. Now we're just timesing these numbers together, so it would just be when the width is highest and when the length is highest. So let's take this this top one here. The highest one is 5.45. So we'll call this the upper bound of the area, 5.45, and the length, or the other one that we've done in blue over here, the upper bound was 4.55. So we're basically taking, when we're multiplying here, we're taking the values that will give us the highest possible area, and that is of course when the lengths are highest, because if we were to have a slightly longer bit here and down on the side here, if this was a tiny bit longer, then we'd get more area out of this rectangle. So we'll leave that there. Anyway, so 5.45 times 5 times 4.55, and the answer to that, just using a trusty calculator, is 24.7975, again meters squared. Okay, so that's should be the highest possible value, and if we think about it, this is the value that we had of just multiplying the standard lengths together that were given to us, and that's actually a little bit lower than this. So this is lower, which is we'd expect, because this here, 24.7975, should be the highest possible value, which is kind of making sense so far, hopefully. What about the lower bound then of the area? Lower bound of area. Well, that would be when the width times the length give the lowest possible area, and that should be when the width is low, so the lower bound of the width, and then the lower bound of the length as well, which should be, well, we're going to do the lower bound here, which is 5.35 times 4.45. So 5.35 times 4.45. And one thing you need to be really careful of here is that you're kind of choosing the right numbers, because it can be easy to get a little bit mixed up. So if you're not following, just wind back. But anyway, from the calculator, 23.8075 meters squared. So that's what we call the lower bound of the area. So the upper bound is that, the lower bound is just 23.8075. So we can say that the range of the area, there we go, range of the area is between the lowest possible value, which is 23.8075, and the highest possible value, which is 24.7975. So these are, and of course these are meters squared. So if we were to go back to our just standard area calculation, 5.4 times 4.5, and remember That's what gave us this 24.3. Does 24.3 exist between these two values? Well, it looks like it does, which kind of makes sense because it should be somewhere in the middle. Okay, so that's bounds and using bounds to calculate areas. However, it does get slightly more complicated, so unfortunately I need to delete this, but you can wind back, as I say. So the next question says that, and this is a kind of a physics based question, but it's very maths as well. So speed equals distance over time. So it's kind of like that speed distance time triangle. Speed equals distance over time, something like that. However, what we've been given as a question says that the distance, and I'm going to call the distance d, so there we go, distance is d, time is t, and speed will be s. So distance equals 30 meters. So what's happened here is, I don't know, something like you're running along, you've run 30 meters, and let's say that the time that took you was 10 seconds to the nearest second and to the nearest meter. Okay, so that's important that you realise that these figures are rounded, because you know it's very, very difficult and it's very unlikely that you run 30 meters in exactly 10 seconds. You know, you stop watch and it might say 9.8 seconds or I don't know, 10.3 seconds or something like that. But to the nearest second is 10 seconds. So what we want to do is work out what is the upper bound or the distance for the upper bound and the distance for the lower bound. Okay, so that's what we're going to do: distance upper bound, distance lower bound, and just sort of calculate what that distance should be. And we're saying that this is to the nearest the nearest meter, so 30 meters. So the upper bound will be 30.5 meters, because anything higher than 30.5 would mean 31. So that would not be 30 meters as a rounded to the nearest meter figure. So that would be our distance upper bound equals that. And what about the lower bound distance? Well, that should be 29.5 meters. Anything less than 29.5 would actually be rounded to 29 meters, which again is not our 30 meters rounded figure. So there we go, we found our distance upper bound, distance lower bound. Now what we're going to do is find our time upper bound. We'll do that first. 10 seconds. Well, what would be the upper bound of that? Well, that should be 10.5. 10.5 seconds is the absolute maximum time before it would actually go to 11 seconds. So 10.5 seconds. And what about the time lower bound? Well, that should actually be 9.5 seconds. Anything less than 9.5, hopefully you're getting the gist, this would round down to 9 seconds. So anyway, we've got our 4 figures here. So I tell you what, we'll circle our upper bounds, lower bounds of all these figures. There we go. So we found the upper bounds and lower bounds of the time and the distance. What we want to do now is find the speed range. The speed range. And what does that mean? Well, that's where we come back to this formula up here. We've got this speed equals distance over time. So speed equals distance over time. So to find the range of the speed, we need to find the lowest, the speed, the lower bound of the speed, to the upper bound of the speed, and that tells us what's the slowest possible speed that was run and the highest possible speed that was run. But in order to find this, let's say we'll take this lower bound of the speed first. We need to figure out what are the values of the distance and the time that gives us the lowest possible value. And it's not just about choosing the lower bound of the distance and the lower bound of the time. That might not work, and in this case it actually won't work. Now, just going to divert just very quickly, and we'll use a different colour for this. I'm just going to do a fraction. This distance over time is a fraction, isn't it, really? It's a division, but it's a fraction. So let's take 100 over 10. We know that the answer to that is 10. 100 divided by 10 is 10. However, if I increase this numerator, let's say it goes to 1000 over 10. Well, this actually makes our answer 100. So as we increase the numerator, there we go, increase the numerator, the answer gets larger. So there we go, answer increases. So what about when we increase the denominator? So let's take this 100 over 10, but let's increase the denominator. Let's make it 100. That actually makes 1. So when the denominator is increased in value, the actual answer, you can see, is reduced. So increase of the denominator equals the answer to be reduced. So actually, to get the lowest possible value, the lower bound of the speed, would mean that this distance would need to be, so here we go, speed lower bound would mean that the distance would need to be at its lowest possible value. Remember, when the numerator increases in value, the answer gets bigger, so we want the lowest possible value, so we need to have the numerator as small as possible. So that would be the lower bound of the distance. The time, however, would need to be the upper bound, because when we increase the value of the denominator, the actual answer reduces. Remember, this 10 went to the 1 as the denominator increased. So we need the lower bound of the distance and the upper bound of the time. Well, we've got these here, haven't we? Lower bound 29.5, upper bound of the time is 10.5. Okay, so that would be the calculation that we'd need to do. Now, what about, and we'll calculate in that in just a second, what about the upper bound of the speed? Well, that must be the opposite case. The distance must be the highest possible, so upper bound of the distance, and the time must be the lowest possible. So that would be the lower bound of the time. So that actually makes 30.5 divided by 9.5. So let's actually calculate these answers, and you can just go ahead and do that on your calculator now if you have one handy. So this says 2.8095, and the lower bound one, that should tell you an answer of 3.2105. So there we go, 3.21, and this is actually in meters per second. Meters per second. So what we have is an answer, or speed range. The lower bound was 2.8095. The upper bound was 3.2105. So the possible speeds that were run were between 2.8 meters per second and 3.21 meters per second, or thereabouts. Now, if we were to just take the original values without bothering about using bounds, then you just do 30 divided by 10, which is just 3 meters per second, and that actually slots nicely somewhere between these two upper and lower limits. So there we go, that is the use of upper and lower bounds, and the use of them in formulas and equations. So it's actually not just quite as simple. Sometimes you need to look at the equation and decide what the possible values could be for the particular variables, the distance and the time in this case, or lengths and widths, or weights, or whatever it might be, and figure out what would give me the highest and lowest possible values for this particular formula. So feel free to have a practice with some of the other work on the CyberTutor website, some of the sheets, downloadable documents and things like that. Thank you very much. Laura, so here's a single bracket expansion. Are you happy to give that a go?
Yeah, would it be 6x plus 5?
No, actually, it's not quite that. Not quite right. Do you want to give it another go?
Oh, was it 3 times 5 as well?
Yeah, 3 times 5 as well.
So it'd be 6x plus 15.
Yeah, perfect. Well done.